Hello friends, IBM is here with another episode of Learning Physics, and this is, remember, this is solved past paper questions. This is specifically AS Physics, paper 2. These questions are quoted from Advanced Structured Questions, that is paper 2, AS. And today I would like to introduce another topic, having seen particle physics. I hope it was interesting. I want us to move to another topic, which is specifically going to be dynamics. The study of physics starts with the mechanics, and the mechanics is both kinematics and dynamics. Your teacher must have told that kinematics deals with describing motion, and you have described motion in terms of words such as acceleration, speed, velocity, displacement, and so on and so forth. You have described motion by using graphs: displacement time graph, velocity time graph, acceleration time graph. You also described motion using the equations of accelerated motion, that is the equations of motion. That was kinematics. In dynamics, we are going to be concentrating on what really affects motion. This is basically force. That's why in dynamics we shall concentrate basically on two major areas. The questions will be relating to Newton's laws of motion and basically linear momentum. So this is part one of dynamics, and straight away let's go to the past paper questions so that we start solving them. So dynamics, when you check in your document, do not forget to download the document. It is attached in the video description. Dynamics is starting on page 139, and straight away we shall start with the first question. Number one, state the principle of conservation of momentum. Principle of conservation of momentum. You will state this principle many times. So the principle of conservation of momentum states that for an isolated system of interacting bodies, the total momentum is always constant. For an isolated system of interacting bodies, the total momentum is always constant. So what do I mean by an isolated system? This is the most important part. An isolated system can also be called a closed system. I could use the word closed system. A system on which there is no net resultant force acting. For such a system, the total momentum of interacting bodies remains constant. That is the principle of conservation of momentum. For an isolated system of interacting bodies, the total momentum is always constant, or the total momentum remains constant. Okay. Two blocks A and B are on a horizontal frictionless surface. The blocks are joined together by a spring as shown here. So we see this is having 4.0 kilograms, 6.0 kilograms. They're joined by a string on a frictionless surface as shown in the diagram. Block A has that mass, block B has that mass. Then the variation of the tension F with the extension X of the spring is shown here. So they have showed us a graph of force and X. Of course, Newton Hooke's law should be coming into your mind. That is, force is equal to K times X. The two blocks are held apart so that the spring has an extension of 8 centimeters. The spring has an extension of 8 centimeters. Show that the elastic potential energy of the spring at an extension of 8 centimeters is 0.48. So this is now Hooke's law. This would be basically in a unit called deformation of solids. but of course we shall still answer it here because it involved the momentum. Okay, so this is a graph of force against extension, that is Hooke's law. And we know that when the spring is extended, elastic potential energy is stored. And we know that elastic potential energy is going to be equal to the area under the graph. The work done in stretching the material, that is the area under the graph, which is the elastic potential energy. And since it is F and X, of course, this is going to be a half times Fx. I can just use the formula half Fx. But remember also that F is equal to Kx. So I could also use a half F. I could also use a half Kx squared. So you could also remember that. But I will straight away use the area. So elastic potential energy is going to be equal to the area, which is a half. And I can take the base to be 8 because that is for 8 centimeters. 8 centimeters is here. So we will find the area under the graph up to around here. So that is 8, but it is in centimeters. So I'll say 8 times 10 power negative 2 to change it to meters. Then times the height, which is going to be this value here on the vertical axis. Just put the ruler. And I think using the scale on the vertical, is 5/10, which is 0.5. So this is 11, that is 12. So on the vertical it is 12. So that is 12, and it is 12.0 newtons. So I check this with my calculator. And straight away I'm getting 0.48 exactly joules. You could use the formula a half kx squared, or you could use a half fx, but this is directly the area under the graph. Unfortunately, since you don't know k, you may not use this directly. It would necessitate you again to first find k, which is again using this formula here. So that is a wastage of time. The blocks are released from rest at the same instant. When the extension of the spring becomes 0, block A has speed VA and block B has speed VB when the extension of the spring is 0. For the instant when the extension of the spring becomes 0, use conservation of momentum to show that kinetic energy of block A over kinetic energy of block B should be equal to 1.5. So since we are using conservation of momentum, it means total momentum before should be equal to total momentum after. So first of all, we know that momentum is mass times velocity. So by conservation of momentum, we shall say that total momentum before should be equal to the total momentum after. So what is the total momentum before? The blocks are released from rest. That means total momentum before was 0. And then total momentum after, immediately when they are released, block A has speed VA and block B has speed VB. But let's look at the masses. Block A had a mass of 4.0. When they are released, block A has a mass of 4.0. That means this momentum is going to be 4.0 now times its velocity VA. And this will be moving, of course, to the right. Block B has a mass 6.0. Its momentum will be 6.0 times its speed, which is going to be VB. When they are released, this will be moving to the left. So the momenta are in opposite directions. So I will put a subtraction sign there. So total momentum after release is going to be 4.0 times VA, that is to the right, plus negative 6.0 times VB, because this negative is because this will be now in the opposite direction. So you are going now to realize that actually VA, when I simplify this, because on the right and the left it is 0, so you realize that VA divided by VB is going to be equal to 4, not 4, 6.0 divided by 4.0. If I simplify that, but we want the ratio of kinetic energy of block A over kinetic energy of block B. We also know that kinetic energy, EK, is a half mv squared. So the ratio kinetic energy of block A over kinetic energy of block B will be equal to a half. The mass of block A is 4.0 times the speed is VA squared, divided by, for B it is a half, the mass is 6.0 times VB squared. So this is a half has already cancelled, I will not take it any further. So this is going to be 4.0 over 6.0 into brackets. We have VA over VB, but this one is also squared. And we have, in the previous part, we have that VA over VB is 6.0. So this will be equal to 4.0 divided by 6.0 times 6.0 over 4.0, and this is squared. And when you simplify this, of course, this one of these cancels out, and 4.0 cancels with 1 over these ones. So this remains, or this gives us a 6.0 over 4.0. 6 divided by 4 is 1.5. So this is going to be equal to 1.5 as required. So that is the ratio. We just played around with simple expressions of AS. Use the information in B Roman 1 and B Roman 2, part 1, to determine the kinetic energy of block A. It may be assumed that the spring has negligible kinetic energy and the air resistance is negligible. So remember, it is the elastic potential energy which becomes kinetic energy of the blocks. So to begin with, remember it is the elastic potential energy which becomes kinetic energy of the blocks. And the elastic potential energy that we found was 0.48 from the previous part. This becomes kinetic energy in A and kinetic energy in B. It becomes kinetic energy in A plus kinetic energy in B. But in the previous part, we have that kinetic energy of A over kinetic energy of B is 1.5. So I will remove 1. Since I want kinetic energy of A, I will remove kinetic energy of B. So so this means that 0.48 is equal to kinetic energy of A. Okay, let me remove kinetic energy of B, since EB in the above equation, or EA in the above equation, is going to be 1.5 times EB. But you can still make you would still make EB the subject and remove it. Let me make EB the subject, no problem. Because I want to remove EB so that I calculate EK directly. From EA, kinetic energy of A over kinetic energy of B being equal to 1.5. This means when I cross multiply, kinetic energy of B is going to be E of A divided by 1.5. I guess that is true. So here I will have kinetic energy of A plus kinetic energy of B is going to be kinetic energy of A divided by 1.5. And I just combine these two, or I can cross multiply or get the LCM, whatever mathematics you use here. Just say 1 plus open brackets. Okay, let me use simple mathematics. I multiply everything by 1.5. So I have 1.5 times 0.48 equals to 1.5 kinetic energy of A plus kinetic energy of A. So when you combine 1.5 plus 1, this means, and then I multiply 1.5 times 0.48. So I have that 0.72 is equal to 1.5 EA of plus EA, that is 2.5 kinetic energy of A. So I just divide 0.5 by 2.5. So this gives me kinetic energy of A as 0.288. So the answer here is going to be 0.288. Yeah, I did a lot of algebra. You can do a simpler algebra. It's just a matter of knowing that the elastic potential energy is what becomes the kinetic energy in the blocks. So the total elastic potential energy becomes the total kinetic energy. And using part A, you notice that this part, you make one of these kinetic energies the subject and substitute in the next part. The blocks are released at t equals to 0. On the figure, sketch a graph to show how the momentum of block A varies with the time t until the extension of the spring becomes 0. So the extension is becoming 0. It is actually decreasing. How does the momentum vary? To take you back to theory, we know that momentum is equal to mass times velocity. We also know that the force is equal to the rate of change of momentum, which means that the change in momentum is equal to force times time. And from here, since I have a graph of F against t, it means the gradient must be the force. The gradient of a graph of momentum with the time must be actually the force. And force, remember, is equal to K times X. What does that mean? They are saying the extension of the spring becomes 0. So the extension becomes 0. And as the extension becomes 0, of course, the force must also become 0. What does that mean? The gradient of the graph of momentum against time should be decreasing and it should be becoming 0. I repeat, because the value of x is decreasing with the time, the force must also be decreasing because the force depends on that extension. And force is the rate of change of momentum. It is, if I plot a graph of momentum with the time, the force is going to be the gradient. Since the force is decreasing, the gradient of the graph of momentum against time should be decreasing from a certain value. Therefore, the graph will therefore be start as a curve whose gradient must be decreasing. It should be starting from 0. And the line must end as a horizontal line. So it's supposed to be a smooth curve, but I try to increase the thickness. Okay, so the curve is going to be a smooth curve whose gradient is actually decreasing. It starts from the origin and it has a decreasing gradient, and the final gradient is 0 because the line becomes horizontal. When the final gradient is 0, it means the force has become 0, since force is going to be at the gradient. The force here is going to be actually the gradient of momentum against time. Okay, so that will be the curve. Two balls x and y move along a horizontal frictionless surface as illustrated here. So this is the initial direction of ball A. I will extend this. I'll also introduce a vertical plane because I know this momentum is in 2 dimensions. So I'll also introduce a vertical plane. As a mathematician, you notice that if this angle here is 60 degrees as labeled, this angle is also 60 degrees. Okay, so let's see the first question. Ball X has initial velocity 3 meters per second in the direction of along line AB. Ball Y has a mass 2.5 kilograms and initial velocity 9.6 in the direction of at an angle of 60 degrees to the line AB. We have seen that in the diagram. The two balls collide at point B. The balls stick together and then travel along the horizontal surface in a direction at right angles to the line AB. So they are moving now as one body with a common speed. So their total mass must be the sum. The mass here is going to be 4.0. Okay, we are going to see the mass, but here they said by considering conservation components of momentum in direction from A to B, show that the ball X has a mass of 4.0, meaning this is 4.0 plus 2.5 total mass here. Okay, let's answer the first part by considering components of momentum in the direction from A to B. In other words, we are going to consider momentum in this direction AB to find this is vertical. We are considering momentum in the horizontal plane here. To find, I've divided this into 2 planes, the vertical plane and the horizontal plane. So by considering momentum in the horizontal plane, we want to find the mass of x. Remember, momentum is mass times velocity. So by conservation of momentum, I will resolve. Initially, this momentum is only in the horizontal plane. So total momentum before collision is going to be the mass, which I want. I will call it m. The mass m. The speed is 3.0. The other one was initially at rest. No, not at all. This was moving towards at an angle that when you resolve this it points to the left. When you resolve y, its velocity in the horizontal axis, it will actually point to the left. So this will be minus. So the mass is 2.5 times the velocity, which is going to be 9.6. When I resolve 9.6 in the horizontal, it will be cos 60. So this is total initial momentum in the horizontal. But after collision, I want you to notice that they all move in the vertical plane. They don't continue in this horizontal direction. That means after collision, total momentum in the horizontal is 0 because they don't move in that direction. So what remains now to solve this expression? So I will just come back here. It's okay, momentum is mass times velocity. Total momentum before collision was m, that is the unknown mass of x, times its speed 3.0. It was moving to the right. Then minus, when I resolved the velocity of y in the horizontal, its momentum was 2.5 times 9.6 cos. Because this in the horizontal was moving towards the left, so this would be cos of 60. And I said the sum of these two was total momentum in the horizontal before collision. But we are seeing that after collision, they don't continue in the horizontal, they are actually moving in the vertical. That's why we said after collision in the horizontal plane, this momentum is 0. So what remains is to solve this equation. So 3m, you take this one the other side, I'll just say 2.5 times 9.6 x cos 60 divided by 3.0, which gives me m as 4.0 kilograms. So the mass of the mass x is 4.0 kilograms. Calculate the common speed v of the two balls after the collision. Of course, after collision, they move in the vertical plane, but um, they move together with the same velocity. So we are still using conservation of momentum. That is total momentum before should be equal to total momentum after. And total momentum before in the vertical plane, remember AB, there was no momentum in the vertical. We are considering vertical motion. X was initially not moving in the vertical. It was only Y moving in the vertical. And Y initially in the vertical, it was actually moving upwards. So when we resolve it vertically, you have y is 2.5 times this speed is 9.6 in the vertical, that is sine 60. That is the total momentum before, because for x in the vertical it was initially 0 because it was moving horizontally. So that is total momentum before collision in the vertical. This should be equal to total momentum after collision in the vertical, and after collision they move in a straight line where they move together. So this is going to be total mass, which is 4.0 plus 2.5 times the speed v. They move with the common speed. Okay, so total momentum before collision in the vertical. We are considering a vertical motion. Total momentum before collision in the vertical is actually 2.5 times 9.6 sine of 60. This was for y, because for x it was initially moving in the horizontal, its momentum was 0. So this should be called total momentum after collision, where they stick together. They move with the common velocity v as shown in the second diagram. So this will be 4.0 plus 2.5 times v. So I just solve this. I think 2.5 times 9.6 sine of 60. I will just divide by the total mass, which is 6.5. And I am getting this v as 3.197 or 3.2. So velocity is 3.2 common velocity. Determine the difference between the initial kinetic energy of ball X and the initial kinetic energy of ball Y. Difference. Remember, kinetic energy is equal to a half mv squared. So let's find the difference in kinetic energy. For ball, initial kinetic energy of ball X, so that is, I think ball X is smaller and ball Y is larger because of the speed. So this is going to be a half times, I'm looking at ball Y, its mass is 2.5, its speed is 9.6 squared. Do not resolve speed when you are finding kinetic energy. Minus the one for ball X, this was for ball Y, minus for ball X, which is a half, times its mass, we have calculated it as 4.0, times its initial speed is 3.0 squared. Whichever you start with, you just need the differences, so you ignore the negative. So I'm checking my calculator. So from my calculator, the difference is approximately 97 joules. You can also verify. State Newton's third law of motion. Newton's third law of motion. People normally wrongly state this law as action and reaction are equal but opposite. That statement is correct, but it is insufficient. If you consider two objects in contact, object A and object B, note that object A exerts a force on object B, and in return, object B exerts a force on object A. These two forces are equal but opposite, and the two forces are always of the same kind, they are of the same nature. So you can simply state Newton's third law by saying the force on body A by body B, force on body A by body B is equal and opposite to force on body B by body A. The force on the first object by the second object is equal and opposite to the force on the second object by the first object. The forces are of the same kind. The two forces are of the same nature. So that is Newton's third law of motion. A block X of mass mx slides in a straight line along a horizontal frictionless surface as shown in the figure. So we see block X, its speed is 5v, block Y, and the block Y is stationary. When they interact, they stick together, as you can see, and move with a common speed v. Use conservation of momentum to show that the ratio my over mx is equal to 4. I think this is an easy question. Total momentum before collision should be equal to total momentum after collision. So we know that momentum is equal to mass times velocity. So I'll use conservation of momentum. The total momentum before should be equal to the total momentum after. So since momentum is mass times velocity, let's start with x. Its momentum is going to be its mass, I'll call it is mass mx, times its velocity, which is 5v. That is the mass of x plus y was at rest, so I'll just put there 0. Total momentum of after collision, they stick together, so the total mass is going to be m of x plus m of y, that is total mass. They move with a common velocity v. So we just now do the algebra. I'm going to divide everything by mx. Everything by mx. Divide this one by mx. Divide here by mx. Divide here by mx. So this side on the left hand side, I remain with 5v equaling to mx over mx, that is 1 plus my over mx. Then this is times v. So I can open the brackets. I have 5v equaling to v plus, okay, v has cancelled both sides without wasting time. V has cancelled because it is a common factor on both sides. So this v has cancelled with the other v. So I now have 5 equals to 1 plus my over mx. So we simply see that my divided by mx is actually 5 minus 1, which is 4. So that is an easy question. Calculate the ratio total kinetic energy of X and Y after collision over total kinetic energy of X and Y before collision. We know that kinetic energy is equal to a half mv squared. So let's find the ratio now. The ratio is going to be for X and Y after collision, so that will be a half. Since they stick together, the total mass is mx plus my times they move with the common velocity v squared. Divide by total kinetic energy of X and Y before collision. Remember, Y was at rest, so I just consider X. So this was a half mx into its speed was 5v, but 5v is squared. So a half has cancelled, and if a half has cancelled, remember my over mx is 4. So this means I'll borrow something from here. I know that my is going to be 4 times mx. I'm going to substitute for my. So this is going to be equal to a half. A half has cancelled, so I have mx plus my. Which my is that? So I have mx plus my, which is 4 mx times v squared, divide by the numerator. I have mx times, this is going to be 25 times 25 v squared. And you also notice that v squared has also cancelled out. So I'm remaining with 5 mx divided by 25 mx. And mx has also cancelled. So I now remain with 1 over 5, which is actually 0.2. So that is 0.2. State the value of the ratio in Roman 2 for a perfectly elastic collision. Note that if it is a perfectly elastic collision, total kinetic energy before collision should be the same as total kinetic energy after collision. Of course, if the two are equal, then the ratio is going to be 1. If the numerator and the denominator are the same, then the ratio will be 1. Total kinetic energy before collision equals total kinetic energy after collision. So that would give us a ratio of 1. The variation with the time t of the momentum of block X in B is shown in the figure here. So this is momentum with the time. Okay. Block X makes contact with block Y at time t equals 20 milliseconds. So we see it starts changing here at 20 milliseconds. That's when it starts changing. But before that, it was constant. So we now answer the question. Describe qualitatively the magnitude and direction of the resultant force, if any, acting on block X in a time interval t equals to 0 to t equals to 20 milliseconds. So between t equals to 0 to t equals to 20 milliseconds, each of us should be able to see that momentum is constant, but force is equal to the rate of change of momentum. When the force is constant, when the gradient is constant, it means the force is also going to be, okay, the force is the gradient or the rate of change of momentum. And since the momentum is not changing, it means the force is going to be 0, the gradient is 0. So that means since force is the rate of change of momentum, then between t equals to 0 to t equals 20, the force is going to be 0. The force is going to be 0 since the gradient is constant. Okay, so let's check the second one. Describe qualitatively the magnitude and direction of the resultant force, if any, acting on block X in the time interval t equals to 20, t equals to 40. So we look at the graph. You notice that t equals to 20 and t equals to 40. You notice that actually the momenta is decreasing. Remember, force is the rate of change of momentum, but the gradient is constant because this is a straight line. The gradient is constant because this is a straight line. So since the gradient is constant, we simply say that the force is going to be constant in magnitude. Constant in magnitude. However, you see that the gradient is negative, so that means it is in opposite direction to the momentum. Constant in magnitude, in opposite direction to the momentum. Okay, next, just a moment. Okay, so we have said that the force here is constant in magnitude, but is in opposite direction to the momentum, simply because the gradient is negative. You can see the gradient is negative and force is the rate of change of momentum. And if the gradient is negative, it means the force is in the opposite direction to the momentum. Okay. On the figure, sketch the variation of the momentum of block Y with the time t from t equals to 0 to t equals to 60. Note that by conservation of momentum, total change in momentum for each of these blocks should be equal but opposite according to Newton's third law. So if block Y was initially at rest when block X was moving with some momentum or with some speed, therefore, when block X was moving with a constant speed before they come into contact, block Y was at rest, so that is zero momentum. I will draw a horizontal line along the x-axis for zero momentum for block Y. So this is in the first 20 minutes, that's what we have as the momentum for block Y. When the momentum of block X starts decreasing, the momentum of block Y should start increasing so that the total momentum becomes the same. So this decreases by, just look at the scale. This decreases by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it falls down by 20 small squares. So this one should also raise up by 20 small squares, but it should stop raising at 40. Or I'll just say 1, 2, 3, 4, 5. I'll subtract 5 from the top. 1, 2, 3, 4, 5. So this will, as the other one falls down by 20 small squares, the other one will increase by 20 small squares, so the total momentum is going to remain the same. When this, after 40 milliseconds, the other one remains constant. After 40 milliseconds, it remains constant for block X. That means even for Y, it should remain constant after 40 milliseconds. So this is going to be a horizontal line. So that is the graph that supposed to draw here. Such graphs are easy as long as you understand the concepts. A ball X moves along a horizontal frictionless surface and collides with another ball Y, as illustrated in the figure. Okay, so we see X and Y, they are moving at an angle before collision. If you want, you can introduce a planes here. I can introduce a vertical plane. Maybe I may need it. Of course, in the vertical, X is acting downwards and Y is acting upwards in the vertical. Because when I extend this one further, that's what we shall be having. Ball X mass 0.3 and angle 60 degrees to line AB. Ball Y mass 0.2. Its initial speed is 6 meters per second, the same angle along to line AB. The balls stick together during the collision and they travel along line AB as illustrated. Calculate to 3 significant figures the component of the initial momentum of ball Y perpendicular, that is perpendicular to line AB, that is in the vertical. Initial component of momentum, the component of the initial momentum of ball Y. So we know that momentum is mass times velocity. So for ball Y, we are going to resolve it to the vertical. If I use this angle here to resolve the speed 6 to the vertical, that is going to be 6 sine 60. So that means the momentum will be mass, which is 0.2 times the velocity, which is 6.0 sine of 60. And when I press my calculator, this gives me 1.039, approximately 1.04, because they wanted the 3 significant figures. By considering the component of the initial momentum of each ball perpendicular to line AB, calculate the 3 significant figures Vx. We are going to consider initial momentum of each ball perpendicular to line AB. We have already seen for ball Y. All we need is for ball X. So remember, momentum is mass times velocity, but we want the component of the initial momentum of each ball perpendicular to line AB. So let's check. Ball X is actually moving downwards. So when I resolve it in the vertical, it will point downwards. So this is its momentum is going to be, when I resolve its velocity, is going to be Vx. Resolving using sine to be, 60 is going to be sine 6, Vx sine 60. So its momentum in the vertical is 0.300 times Vx sine 60. And this is pointing downwards. Yet the other one is pointing upwards. So by conservation of momentum in the vertical, this is going to be equal to 1.04. The momentum of ball Y in the vertical is upwards. Ball Y, its momentum is going to be upwards. Ball X, its momentum is going to be downwards. So by conservation of momentum in the vertical plane, they are going to be equal. So I can now find Vx. Vx is going to be 1.04 divided by 0.3 times sine of 60. So this is giving me 4.00, because they wanted the 3 significant figures. So that is 4.00. Show that the speed of the two balls after the collision is 2.4. Of course, after the collision, they're moving in the horizontal plane. I'll only consider momentum in the horizontal. When I resolve Vx in the horizontal to be Vx cos 60, resolving 6 to the horizontal to be 6 cos 60, and those will point in the same direction, that is to the right. And after collision, they are also moving to the right. So that means I will just conserve momentum in the horizontal plane. So for x, that will be 0.3 times Vx, which Vx I have got as 4.00. That's total momentum of x in the horizontal. But remember, it was moving at an angle of 60, so I have to say velocity times cos of 60. Then plus, the second ball will be, its mass is 0.200 times its velocity, which is 6.00 cos 60. That is total momentum before collision in the horizontal. After collision, they stick together, so their masses are added up. So we have 0.30 plus 0.20, then times the common velocity v. I'll just simplify this on the left hand side. Open bracket, 0.3 times 4 cos 60 plus 0.2 times 6 cos 60, 1.2. So I have that 1.2 on the left equals to 0.50 times v. So 1.2 divided by 0.5. That means v is equal to 2.4 as required meters per second. So that is the speed. The two balls continue moving together along the horizontal frictionless surface towards a spring as illustrated in the figure. So we see they are moving towards the spring with the speed 2.4 meters per second. The spring constant is that. Of course, we know what will happen when they collide with the spring. Of course, the spring is going to be compressed. The balls hit the spring and remain stuck together as they decelerate to rest. That means they lose all their kinetic energy. In other words, their kinetic energy is going to become elastic potential energy in the spring. All the kinetic energy is converted into elastic potential energy of the spring. The energy E stored in the spring is given by that expression. K is the constant, which is the spring constant, and X is the compression. The spring obeys Hooke's law and has a spring constant 72 newtons per meter. Determine the maximum compression of the spring caused by the two balls. Since all the kinetic energy is converted to elastic potential energy, we know that kinetic energy E is a half mv squared. So this one will be equal to a half kx squared because all the kinetic energy becomes elastic potential energy. So I'll just substitute. Total mass is 0.5 because they stack together times the speed, which is 2.4. That is the initial kinetic energy times a half, of course, is equal to a half as cancelled. I've cancelled out this one. So K is 72 times x squared. So just have 0.5 times 2.4 squared divided by 72 square root. So I'm getting the answer here as 0.20 meters. You can check. On the figure 4.4, sketch graphs to show the variation with the compression x of the spring from 0 to maximum compression of the magnitude of the deceleration A of the balls. Since the ball follows Hooke's law, we know Hooke's law F is equal to K times X. As the compression increases, the force increases. And the force, remember, is mass times acceleration. So the force, the mass acceleration is increasing. So that is going to be, that means the extension is directly proportional to the acceleration, and they're in the same direction. So that is going to be a straight line. When the extension, when the compression is zero, the force is zero, the acceleration is zero. When the compression increases, the force increases, the acceleration increases. So this is going to be a straight line. Then the kinetic energy EK of the ball. Remember, the kinetic energy is directly proportional to the elastic potential energy. Kinetic energy decreases as kinetic energy decreases as the elastic potential energy increases. EK decreases as the elastic potential energy increases when the compression increases. And we know that elastic potential energy increases as compression increases. So as compression increases, the elastic potential energy increases, but the elastic potential energy increases as the kinetic energy decreases. What does that mean? Since the elastic potential energy is directly proportional to x squared, it means that a graph of kinetic energy against x is not going to be a straight line. It is going to be a curve. In other words, as x increases, the kinetic energy decreases rapidly. If I'm to put it, because x increases, because it is squared, it is going to increase rapidly. It is going to make kinetic energy to decrease more rapidly, since they are inversely proportional. Therefore, this is going to be a curve. There is an initial kinetic energy because there is an initial speed, but as the compression increases, the kinetic energy decreases, the elastic potential energy increases. So this is going to be a curve of this nature. The gradient is increasing, and the gradient is going to be positive. Is it positive? The gradient is increasing because the line is becoming steeper. So the line is going to have a positive value because the initial kinetic energy was not zero. But as compression increases, the kinetic energy decreases because the kinetic energy is lost as it is being converted into elastic potential energy. But remember, elastic potential energy is equal to half kx squared. So it means the kinetic energy is going to decrease more rapidly as x increases. Hence, it is going to be the line is going to have an increasing downward slope, and it is of course going to stop on a positive value of x, where when x becomes zero, when kinetic energy becomes zero, then the compression must be maximum. A ball B of mass 1.2 kilograms traveling at constant velocity collides head-on with a stationary ball S of mass 3.6 kilograms as shown here. Frictional forces are negligible. The variation with the time t of the velocity of the ball before, during, and after colliding with the ball S is shown here. So here they have showed us variation of velocity with the time. Before, during, of course, before the velocity is constant, during the velocity is reducing and there's been a change in direction, and after it again remains constant. So there's a horizontal axis here. State the significance of positive and negative values of V. Of course, positive and negative values of V means that the ball is moving in opposite directions after collision. So the ball is moving in opposite direction after collision. I said yesterday that I said in nuclear physics, I mean in particle physics, that the word different does not replace opposite. Saying different direction is not the same as saying opposite direction. So the negative and positive values means that the ball is moving in opposite direction, in the opposite direction after collision. Then use the figure to determine for the ball during the collision with ball S, the change in momentum. Of course, momentum is mass times velocity. Now we want the change in momentum. So change in momentum is going to be the mass. Let's begin by the mass of the ball. The mass of ball B is 1.2 because this graph is for ball B. So that is 1.2. Change in velocity. Before coming into contact, the velocity is 4, positive 4, minus. After coming in contact, the velocity is, what is this value here? This is the value which is the scale on the vertical is 0.1 divided by 5, that is 0.2. So this is going to be 0.8 negative. So that is minus negative 0.8. And this gives us, so we have 4 plus 0.8 times 1.2. So this is giving me 5.76. So the change in momentum is 5.76. Do not forget the minus and the negative sign on that. Then the magnitude of the force acting on ball B. By definition, force is the rate of change of momentum. So force is equal to change in momentum with time. And the change in momentum is 5.76 divided by time. The time between which momentum changes. So we are starting from this point here. And it stops changing at this time here. On the x-axis, the scale is 0.01 because it's 0.1 divided by 10 boxes, 0.01. So here we have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 0.1, 0.2. So we are starting from here. That is 0.18 up to 0.21, 22, 23, 24, 25, 26. So we subtract 0.26 minus 0.18. So the time is 0.08. So we divide by 0.26 minus 0.18. That is the time of contact, which is 5.76 divided by 0.08. When I press my calculator, this is going to be 72 newtons. So the force is 72 newtons. Calculate the speed of the ball S after collision. Speed. Now, of course, we now employ Newton's third law. By Newton's third law, if we employ Newton's third law, it means the change in momentum is equal but opposite. So change in momentum is the same. By Newton's third law, the change in momentum is the same. So it means 5.76 is equal to mass, which is 3.6 for ball S, times its speed v. Because the change in momentum is the same, so I'll just divide 5.76 by 3.6, which is 1.6. So the speed v is 1.6 meters per second. Using your answer in C and information in the figure, deduce Reduce quantitatively. Quantitatively means you must have some values. Reduce quantitatively whether the collision is elastic or inelastic. Okay, so to find whether the collision is elastic or inelastic, there are two ways. You can look at kinetic energy, or you look at the speeds of approach and the speed of separation. I'll use speed of approach. So the relative speed of approach equals to, the other one was at rest, and this was moving at a speed of 4 meters per second. So the relative speed of approach is 4 minus 0, which is 4. Then the relative speed of separation this one was after separation. This is moving at negative 0.8 or 0.8 in one direction, and the other one is moving at 1.6. So the relative speed of separation is going to be 1.6 minus negative 0.8, which is 2.4 meters per second. So this is inelastic since the speeds are not the same. So inelastic. Alternatively, you can find kinetic energy, total kinetic energy before collision. This is another alternative. Total kinetic energy before collision is going to be a half times the mass. It is ball B which was moving. The mass was 1.2 times its speed, which is 4. Check. It is 4 squared. So 4 squared times 1.2 divided by 2. So initial kinetic energy before collision is 9.6 joules. Then total kinetic energy after collision. After collision, the other one moves with a speed of 0.8 in the opposite direction. So this is going to be a half times the mass is 1.2 times 0.8 squared plus a half times the second one has a mass of 3.6. Its speed is 1.6 squared. Let me check this. 0.8 squared times 1.2 divided by 2 plus 0.5 times 3.6 times 1.6 squared. So this one gives me 4.992 joules. So you see that kinetic energy before collision is not the same as kinetic energy after collision, so this is inelastic. In other words, kinetic energy is not conserved, so the collision is inelastic. The variation with extension x of the tension F in a spring is shown here. So this is almost Hooke's law. Use figure 3.1 to calculate the energy stored in the spring for extension of 4.0 centimeters. 4.0 centimeters. Energy stored is the area under the graph. So I'll use the ruler here. So this is 4.0, and 4.0 corresponds with this value here, and I think this is 180 from the scale. So we want to calculate the energy stored. So energy from dynamics, deformation of solids, energy is equal to the area under the graph. The area under the graph, or you can use a half F times X. So energy is going to be a half times X, which is 4 centimeters. That is 4 times 10 power negative 2 times the height is going to be 180. So I just press my calculator. From my calculator, the energy is 3.6. The spring in A is used to join together two frictionless trolleys A and B of mass M1 and M2 respectively, as shown here. The trolleys rest on a horizontal surface and are held apart so that the spring is extended. The trolleys are then released. Explain why, as the extension of the spring is reduced, the momentum of trolley A is equal in magnitude but opposite in direction to the momentum of trolley B. Remember, the trolleys are what? The trolleys rest on the surface and are held apart so that the spring is extended. The trolleys are then released. So if you think of a conservation of momentum, before release, their total momentum is actually zero. So after release, the total momentum should still be zero. Therefore, they are going to be moving in opposite direction. So the momentum must be in opposite direction. Therefore, the easiest way to think about this is that a total momentum before release is zero. Total momentum before release is zero. Total momentum before release is zero. So the sum of momenta of the trolleys, momenta is now plural. The total sum of the momenta of the trolleys should also give us zero. So the sum of momenta of trolleys must be zero after release. Must be zero after release. So the sum of momenta of the trolleys must be zero after release. And if the sum of the momenta is to be zero, they must be in the opposite directions. So we say that so momenta should be equal, first of all, but opposite, so that the total after is still zero. So that the total after is still zero. So because before release the total momentum was zero, then after release we also aim at having total momentum to be zero. So they must be moving in opposite directions. That means the velocities are going to be in opposite directions. That means the momenta of the trolleys are going to be in opposite directions. And if they are equal in magnitude, then their total is going to be equal to zero. That is conservation of momentum. Alternatively, you can use Newton's third law, where you just mention force is equal to the rate of change of momentum. And the forces on trolleys are equal and opposite by Newton's third law. So the force is equal to change in momentum. the forces, the force on trolleys are equal and opposite by Newton's third law. This is another way of thinking about this. By Newton's third law, the forces on the trolleys are going to be equal but opposite. And if the forces are equal but opposite, but force is the rate of change of momentum, as long as the time is the same, then the change in momenta are going to be equal but opposite. Okay. At the instant when the extension of the spring is 0, trolley A has a speed v1 and trolley B has a speed v2. Write down an equation based on momentum to relate v1 and v2. At the instant when the extension of the spring is 0, remember the momenta are equal but opposite. Write down an equation based on momentum to relate v1 and v2. So it means m1 v1 is going to be equal to m2 v2 by conservation of momentum, because when the extension is 0, the total momentum, remember, must always be conserved, and the momenta are equal but in opposite directions. So m1 v1 should be equal to m2 v2. Then write down an equation to relate the initial energy stored in the spring to the final energies of the trolleys. So initial energy stored in the spring E is equal to the final energies in the springs. So that is going to be kinetic, a half m1, its speed is v1 squared, plus the other one is going to be a half m2, its speed is v2 squared. So for speed we don't put there minus, because for energy we shall not put there minus, because energy is a scalar quantity. Show that the kinetic energy EK of an object of mass m is related to its momentum by that expression. This is simple mathematics. From AS, we know that kinetic energy EK is a half m v squared. And when I multiply both sides, I cross multiply, this becomes twice EK equals to m v squared. I multiply both sides by m, it becomes twice m EK. This side also by m, it becomes m squared v squared. But remember, momentum is equal to mass times velocity. So this one is p squared. So we have that twice m EK is equal to p squared. Hence, EK is going to be p squared divided by twice m. So that is a simple expression. Trolley A has a larger mass than trolley B. Use your answer in Roman in 2 part 1 to deduce which trolley A or B has the larger kinetic energy at the instant when the extension of the spring is 0. Trolley A has a larger mass. Remember, momentum equals to mass times velocity. Trolley A has a larger mass than trolley B. What does that mean? If B has a smaller mass and yet momentum is mass times velocity, so B and remember, momentum must be the same. So B must have more speed, and therefore it should be having a greater kinetic energy. So momentum is mass times velocity, and we want to use our answer to deduce which trolley A or B has a larger kinetic energy. So if momentum is mass times velocity and yet B has a smaller mass, and since momentum is the same, B has a smaller mass, and since momentum is the same, P is the same, but the mass is smaller. It means kinetic energy is going to be greater, so V is going to be greater. So Since momentum is the same, B has more velocity, thus kinetic energy is greater for B. On the other side, you can look at A. Since A has a larger mass and momentum is the same, so A will have less speed. It will have a smaller kinetic energy because momentum is the same, but the mass is greater. If the mass is greater, it means the kinetic energy is going to be small for A. So A will have a smaller kinetic energy if the momentum is the same because it has a greater mass. Define force. At this point, you should be able to define force as the rate of change of momentum. At this level, you can't define force as a push or pull. So force is defined as the rate of change of momentum. Rate of change of momentum, that is force. The Newton's third law should now be you should be familiar with it. Force on body A by body B is equal in magnitude to force on body B by body A, but the forces are in opposite directions. The forces are in opposite directions. The forces are of the same kind. In other words, the forces are identical. I was aiming at the 3 marks. That's why I had to add that the forces are identical or the forces are of the same kind. Whenever two bodies interact, body A exerts a force on body B, and body B exerts an equal but opposite force on body A. The two forces are always of the same kind. Two spheres approach one another along a line joining their centers as illustrated here. When they collide, the average force acting on sphere A is Fa and the average force acting on sphere B is Fb. Fa is acting on sphere A, Fb is acting on sphere B. The forces act for a time Ta on sphere A and Tb on sphere B. State the relation between Fa and Fb. We have just mentioned Newton's third law. The forces are equal but opposite. So we simply say that Fa is equal to negative Fb. The negative is going to indicate that they are in opposite directions. Then Ta and Tb, the time of contact is always the same. So we say Ta is the same as Tb when they are in contact. Then use your answer in Roman 1 to show that the change in momentum of sphere A is equal in magnitude and opposite in direction to change in momentum of sphere B. Of course, we know that force is equal to the rate of change of momentum. And we know that change in momentum, therefore, is going to be force times time. That is the change in momentum. But remember, the forces are equal but opposite, and the time is the same. The forces are equal but opposite, and the time is the same. So for A, the change in momentum for A is going to be the force, which is Fa times Ta. And the change in momentum for B is going to be equal to Fb times Tb. Remember, Fa and Fb are equal but opposite, and Ta and Tb are the same. Hence, we just conclude that Fa times Ta is equal to negative Fb times Tb, which is the change in momentum of A is equal, the minus is showing opposite direction, the change in momentum of Fb. So this is the statement which the examiner is looking for. For the spheres in B, the variation with the time of the momentum of sphere A before, during, and after collision with the sphere B is shown here. So they have showed us here graphs, which are a graph which is incomplete, and they are telling us to complete the momentum of sphere B before the collision is also shown in the figure 3.2. So you see it is incomplete, it stops somewhere here. Yet this one is here. It means we have to extend this. The sphere B should also be, when sphere A's momentum is still constant, sphere B should also be still constant. So this is up around here. So we have to extend this graph up to here. When the momentum of sphere A starts decreasing, then the momentum of sphere B should be increasing, and they should be in opposite directions. So the change in momentum, this one falls by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the other one should also increase by 18 small squares. So they are going to meet at the same along the same vertical, along the same point by 18 small squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 is around here. So the other momentum will also increase up to that point. Remember, total momentum must remain conserved. So you must be very careful when you're drawing this. So it should be here. Okay. Then when the momentum of sphere A remains constant up to this time here, the other one should also remain constant up to the same time. So I'll draw a horizontal line. So that is my graph. So you must be very careful here when you are sketching this graph. An easier way to do this, normally my students tend to find better ways of doing this. So total momentum is going to be using this. Above it was 6, for A it was 6 plus, below it was negative below it was -4. -4, and the total is 2. So total momentum should always be 2. And then the total momentum should remain 2. So here at the bottom for sphere B, it is, what is this total momentum? This is 1, 2, 3. No, the other one was -3 plus x should give us 2. 1, 2, 3. 6 plus -3, that is 3. So this is 4, -4 plus x should give us 2. So x is going to be equal to 6. So that means I will add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will stop at, anyway, whatever method you use, all that you need is to note that when the momentum at this point here, it is falling, it falls by this magnitude, it should increase by the same magnitude, and it stops increasing at the same time where it stopped going in the other direction. So that is the most important part. My students have an easier way of arriving at that sketch. But in all cases, you will notice that the total momentum is remaining constant. That's what is very, very important. Total momentum remains constant. Okay. A ball is thrown vertically down towards the ground with an initial velocity of 4.2 meters per second. The ball falls for a time of 1.51 seconds before hitting the ground. Air resistance is negligible. Show that the downward velocity of the ball when it hits the ground is 19.0 meters per second. I think this is kinematics, but since it is overlapping with dynamics, we can't leave it unattempted. So using the equations of motion, it is thrown vertically downwards. Vertically downwards. So V is equal to U plus at. It starts with a certain velocity, which is 4.23. Since it is falling downwards, G is positive, so plus 9.81, and it takes a time of 1.51 seconds. So that one, you just press your calculator. And this is 19.04 meters per second, which is approximately 19. Calculate to three significant figures the distance the ball falls to the ground. So S is equal to UT plus a half at squared, because I want a distance. So our initial velocity is 4.23. The time it takes is 1.51 plus a half times 9.81 times the time, which is 1.51 squared. So this is simple substitution. I just substitute. So for my calculator, I'm getting this as 17.6 meters. The ball makes contact with the ground for 12.5 milliseconds and rebounds with an upward velocity of 18.6 meters per second. The mass of the ball is 46.5 grams. Calculate the average force acting on the ball on impact with the ground. Average force. So you need to note that average force is going to be got from the idea of change in momentum, and force is equal to the rate of change of momentum. All we need is the change in momentum, and note that momentum is mass times velocity. So this is going to be change in momentum, which is mass, times change in velocity. I'll say v2 minus v1 over time t. The mass is 46.5 grams, which is 46, divide this by 1,000. So that will be 0.0465 times the change in velocity. It rebounds. That means it moves in the opposite direction. So this is going to be 18.6 minus negative because of rebounding. That is in the opposite direction. The initial velocity is 19. So this is going to be minus negative 19.0. Then divide by the time of contact, which is 12.5 times 10 power negative 3 to change it to seconds. So when I press my calculator, so from my calculator, this is approximately 140. And of course, since it was falling vertically downwards, if it rebounds, the direction is going to be upwards. Calculate the average force acting on the ball on impact with the ground and the direction of the force. Of course, the ground exerts a force on the ball. Use conservation of energy to determine the maximum height the ball reaches after it hits the ground. So we are using conservation of energy. So the loss in gravitational potential energy, the loss in potential energy should be equal to the gain in kinetic energy, or the other way around. The ball makes a contact with the ground and rebounds. So let me do it the other way around. When it is moving upwards, it is losing kinetic energy. So it will be the loss in kinetic energy is equal to the gain in potential energy. So that is going to be a half m v squared should be equal to m gh. So m has cancelled. So I just substitute. I know that h is going to be a half times v. Of course, it moves upwards with velocity 18.6. So v is 18.6 squared divided by g, which is 9.81. So this is 17.6 meters. State and explain whether the collision the ball makes with the ground is elastic or inelastic. We can check. We can check if kinetic energy is conserved, but you see that it was falling with a speed of 19 meters per second and it rebounds with a speed of 18.6 meters per second. That means kinetic energy is not conserved. And if kinetic energy is not conserved, then it means the collision is inelastic. So we say that kinetic energy of the ball is not conserved. So kinetic energy of the ball is not conserved on impact or on collision. So inelastic. Alternatively, you can look at the speed before impact and the speed after impact. They are not the same. Or you can look at the speed before impact is not the same as the speed after impact. So the collision, so it is inelastic still. The collision is inelastic. So define force. By definition, force is the rate of change of momentum. The rate of change of momentum. The resultant force F acts on an object of mass 2.4 kilograms. The variation with the time t of F is shown in the figure. So they have given us a graph of force against time, as you can see it here. So the question wants us on the figure 2.2, which is at the bottom here, show quantitatively, that is, you must quote values. Show quantitatively the variation with the time t of the acceleration a of the object, include appropriate values. Let's first find the acceleration here between t equals to 0 to t equals to 2. You see that the force is constant, so force resultant force is mass times acceleration. The acceleration is going to be, what is this value here? I think this is 8.4. So the acceleration is going to be 8.4 divided by the mass. The mass was given as 2.4. So the acceleration is 3.5 meters per second squared. That is between t equals to 0 to t equals 2.5, the acceleration is constant, 2.5. Then between t equals to 2.0 to 4.0, the force is constant and 0. Then the acceleration here is 0. So this part, acceleration is 0. This part, acceleration is 3.5. So let's choose a scale here. Of course, the other part after 2.0, I'll just drop 9 because the acceleration there is 0. So that part, the acceleration is 0. Then this other part, I will choose a scale. Let me say after every 10 small squares, I put there a mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here. So I'll say this is 1.0, 2.0, 3.0, and 4.0. So I'm looking for 3.5. I think 3.5 is in the center here. 1, 2, 3, 4, 5. That is 3.5. So, and it is constant. The acceleration is constant, and it is 3.5. So that will be the graph for acceleration against time. So this is at 3.5 is the acceleration there. Okay, so that is a simple graph. You're just using a force is mass times acceleration. Where the force is 0, the acceleration is 0. Where the force is constant, the acceleration is constant. You just needed to find it. Okay, next. On the figure 2.3, which is here below, show quantitatively, meaning we have again to calculate the variation with the time t of the momentum p of the object. Include appropriate values on the y-axis. We want momentum this time. Remember, force is the rate of change of momentum. Force equals the rate of change of momentum. So it means the change in momentum is going to be equal to force times time. So for the first 2.0 seconds, the change in momentum is going to be the force from the graph. The force from the graph was 8.4. So for the first 2 seconds, the force from the graph was 8.4. So that will be 8.4 times the time, which is 2. So the change in momentum is going to be equal to, this is going to be 16.8 Newton seconds. Newton seconds. That is the change in momentum for the first 2 seconds. Remember, force is the rate of change of momentum. When the force is constant and not zero, it means the change is increasing, or the velocity is increasing uniformly by equal time intervals. So it means the momentum is increasing by equal time intervals, and in that time, the change must be 16.8. Then, of course, for the other part, the change in momentum for the other part is going to be 0. After 2.0 seconds, the change in momentum is going to be 0. So that means the graph will be a horizontal line. So we just look for a scale on the vertical. So I will say after every 10 small squares, that will be maybe 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is going to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is going to be 15, and this is going to be 20. So for the first 2 seconds, the change in momentum is 16.8. So I look for 16.8. The scale on the vertical is each small square is 0.5. So this is 15.5, 16. 16.5, 16.8 is in the center here. 16.8 is somewhere here. So this is going to be a straight line from the origin. Remember, the gradient is the force. And if it is a straight line, the gradient is constant and not 0. So the force is constant there and not 0. Then after that, the force is 0. So after that, the gradient is going to be 0. So I draw a horizontal line. So the graph is going to be somewhat like that. So when acceleration is constant, of course, we know when acceleration is constant, the velocity increases uniformly, so momentum is increasing uniformly. When the change when the momentum is constant, it means the rate of change is zero, the force is zero. So when force is zero, the momentum is constant. When force is constant and not zero, the momentum increases by equal amounts in equal time intervals. So you can think about it like that. Okay, I hope this is correct. 16.8, how many squares are those? 16.8 divided by 0.33. 10, 20, 30, 31, 32, 33, and almost a half, yes. So that is the okay. State the principle of conservation of momentum. Now we know that total momentum, the total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting bodies is always constant. State the difference between an elastic and inelastic collision. Of course, we know for elastic, total kinetic energy is conserved, but not for inelastic. So for elastic, total kinetic energy is conserved, but not for inelastic. So that is the major difference. For elastic collision, total kinetic energy is conserved. For inelastic collision, it is not conserved. An object A of mass 4.2 kilograms and a horizontal velocity 3.6 meters per second moves towards object B as shown in the figure. So we see the speed of A, the speed of B, they're moving in opposite directions. Remember, when you are dealing with the momentum, direction is very important. Object B of that mass is moving with the horizontal velocity towards object A. The objects collide and then both move to the right as shown here. So this is after collision, they move to the same side. Calculate the velocity v of object A after the collision. So we know the momentum is mass times velocity. We are going to conserve momentum. So total momentum before collision should be equal to total momentum after. So total momentum before collision, we come back here. It is going to be 4.2 times 3.6 minus, because this is in the opposite direction, 1.2 times 1.5. So this is going to be 4.2 times 3.6 minus 1.2 times 1.5 should be equal to, after collision, they move in the same direction, so the total momentum will be 4.2 times the velocity v for A plus 1.5 times the velocity 3.0 for B. So we now I will just press the calculator from here. As a mathematician, there is nothing to make the subject here. Just pick your calculator, 4.2 times 3.6 minus, open bracket, 1.2 times 1.5, again minus, open another bracket, 1.5 times 3, divide by 4.2. That is 2.1. So V is 2.1. Determine whether the collision is elastic or inelastic. You can check this using kinetic energies. You can check this using relative speed of approach. So I'll use kinetic energy, total kinetic energy before collision. I'll call it E1. This is going to be a half times the mass of body A. I'm just using the expression for kinetic energy. Okay, let me just write mass of A, speed of A squared, plus a half mass of B, speed of B squared, which is going to be, for A it is a half, mass of A was 4.2, the speed of A was 3.6 squared, plus a half, mass of A, which is mass of B, which is 1.5, speed of B, which is 1.2 squared. You don't need to put a minus here when you are dealing with kinetic energy. So find total kinetic energy here. So here this gives me total kinetic energy as 28.28 joules. Then after collision, total kinetic energy after collision is going to be a half. A is times 4.2. Speed of A after collision is 2.1 squared plus a half. B is 1.5 times speed of B after collision, which is 3.0 squared, which is going to be 4.2 squared, 4.2 times 2.1 squared plus 1.5 times 3 squared. So this is giving me 16 joules. So kinetic energy, you see that the values are not the same, so kinetic energy is not conserved. Kinetic energy is not conserved. So inelastic. So that is method 1. Method 2, we can use relative speeds. So I'll check the relative speed of approach. That is the difference with which the bodies are approaching, the difference in the velocities when they are approaching. So this is going to be 3.6 minus negative 1.2, which is 4.8. So relative speed of approach is 4.8 meters per second. Then the relative speed of separation equals to, they move in the same direction with the same speed, so I just subtract without minding about which one is greater. I just say 3 minus 2.1, which is 3 minus 2.1, which is 0.9 meters per second. So you notice that the relative speeds of approach are not the same, so inelastic. So you can choose either to explain with relative speeds of approach and relative speed of separation, or you can choose to explain with kinetic energy. If the kinetic energy is not conserved, the collision is inelastic. Okay, so state Newton's first law of motion. I want to stop with this question. State Newton's first law of motion. So we know that a body continues at rest The body continues at rest or moving with uniform velocity unless acted on by a resultant force. The word resultant here is very important. The body continues at rest or it continues moving with a uniform velocity unless acted upon by a resultant force. That is Newton's third law. I beg to stop here and we shall start from this particular question and part B on the next page. Thank you. I hope you learned something from these questions. In case you have any challenge or is inbox, don't forget, download the document, print, you can print per topic and follow with the videos. Thank you and stay blessed.